Hello. Well, you'll be relieved to hear this is almost the end of the new worm servo saga. This is episode 5, and there might be one more when I put the new servo in its waterproof box. Excuse me, what are you doing, ducks? This episode is about the software that drives the brushless motor, reads the Bourne's encoder, and works out what to do on the basis of a PWM signal from the autopilot. Well, I'm just testing the software for this new rudder servo. So here's the new rudder servo. It's driven from a Teensy 3.2, which is an Arduino equivalent here. This pink wire is a USB programmer for the Teensy, but it's actually not plugged in at the moment. And this, the software in here expects to receive a PWM signal from the autopilot to tell it where to put the rudder. And that PWM signal comes via this radio control box, which we've always had on the stern of Woodstock. It contains a radio control receiver with an extended aerial and a changeover relay. And the changeover relay either connects a PWM signal from the RC receiver to the rudder servo, or it connects a PWM signal from the autopilot to the rudder servo. As I haven't got an autopilot on the scene at the moment, I'm using this signal generator to simulate the PWM signal from the autopilot. And of course, the PWM signal from the RC receiver comes from this transmitter here. And by operating this switch, I can operate the changeover relay and either drive the rudder servo from the remote control or from the simulated autopilot. There are 3 power supplies here. This 5-volt supply on the right, whose current is measured in milliamps here, is driving the Teensy and the Bourne's EMS22 rotary encoder. There's a 12-volt supply here which is driving the brushless motor. And then there's another 5-volt supply here which is driving this RC box, whose consumption I'm not interested in at the moment because we only use it for test purposes. So the 2 power consumptions that are interesting is the current consumption on the 5-volt line driving the Arduino, which is 3 milliamps at the moment, and the current consumption on the 12-volt line driving the brushless motor, which is 5 milliamps when nothing is happening. So the circuit I've got here is this brushless motor, which is driven from a Teensy 3.2, which only needs to control a PWM signal, which is either fully on or fully off, and a direction signal, which is either 0 or 1. The Teensy 3.2 takes a PWM signal from the autopilot, measured its width, and acts accordingly. There is a Bourne's EMS22A rotary encoder, which is connected by an SPI interface to the Teensy, and because this thing takes 20 milliamps all the time, I have switched its power via these two, this FET and this transistor. So you've got 5-volt power coming in here, which is switched by this transistor, and so the encoder is only turned on when I actually need to know where the rudder is. So that saves a standing current of 20 milliamps. So if we change the pulse width of the PWM signal, assume this is the rudder pointing that way, central, it can go around to plus 90 degrees, or minus 90 degrees. It's going in jumps there because the signal generator is moving in steps of 0.1 milliseconds. So if we turn on the radio control transmitter, it actually is on, and operate the switch to operate the changeover, we'll get the PWM signal from here rather than from the signal generator. So I do that. You should see a change on the oscilloscope here, because it's a lower frequency as it happens that comes out of here. And now we can control the rudder with the joystick. And if I set min-max on this current, we should find, so the maximum current on to the brushless motor is 110 milliamps when it's actually moving, and the current to the Arduino remains about 3. Well, actually no, it goes up, the current to Arduino goes up to 17 milliamps when the rudder is actually moving, but it's 3 milliamps when it's stationary. So there's an 8 milliamp standing current draw when the rudder is doing nothing, whatever position it might be in. And then it peaks at 110 milliamps on the 12 volt line and 16 or 17 milliamps on the 5 volt line when the rudder is actually moving. The software controlling this motor is not sophisticated at all. It doesn't use a PID algorithm or anything of the kind. It simply turns the motor on full speed, monitors the position of the rudder every 10 milliseconds until it gets within 2 degrees of where it's been told to go, and then it just turns the motor off. And that seems to work reliably. It does give there's a kind of 2-degree deadband built into this software, which if the rudder's in a particular position and the PWM command signal tells it to go to some other position that's within 2 degrees of where it already is, it just ignores it, because I don't want the thing constantly jittering around like that. That does mean that if I move the joystick very gradually, the rudder moves in jumps. It's hard to move it. But on the other hand, it's reasonably responsive when one makes large movements. I think the deadband is worth having to avoid unnecessary wear on the mechanicals. The main control loop of the Arduino software is shown here. It reads the PWM input signal and measures its width, tests that width for sanity, and if it's okay, converts it to a desired rudder angle. It then clips that rudder angle to rud max, which is set at 90 degrees, just to prevent us driving the rudder backwards. It then tests to see if the desired rudder angle is within 2 degrees of the current rudder angle, deadband here is set to 2, and if it is not within 2 degrees, it tells the motor to move to the required angle. If it is within 2 degrees, it just comes out of the loop without doing anything, and then repeats until that condition is met. And then basically it just goes to sleep for 1/10 of a second. That's to save current consumption, using the snooze module, which lowers turns off most of the Arduino. And it has to wake up periodically to see whether the PWM signal has actually changed. The actual motor moving software is here. It has a counter just to stop itself getting locked indefinitely in this loop. It basically just reads the angle of the rudder, calculates the difference. If the difference is less than 2 degrees, it comes out of the loop. If it's greater than 2 degrees, it sets the direction to clockwise or anti-clockwise, turns the motor on at full speed, waits for 10 milliseconds and repeats. And when it comes out of the loop, it turns the motor off. So incredibly simple. Going back to July 2017, when I tested a good Savox brushless servo, we found that its current consumption at 5 volts was 43 milliamps when it was stationary and 378 milliamps when it was moving. Compare that with the new brushless worm servo, which takes 3 milliamps at 5 volts and 5 milliamps at 12 volts when it's idle, and 17 milliamps at 5 volts and 110 milliamps at 12 volts when it's moving. So comparing these in terms of power, the new worm servo takes 75 milliwatts when it's idle, compared with 215 milliwatts from the Savox. And when it's moving, the new worm servo takes 1.4 watts compared with 1.9 watts from the Savox. I also measured the torque, and to stall the new servo it takes 10.5 kilograms force centimeters, whereas it takes 8.4 to stall the Savox. And to move the new worm servo by pressing on the rudder takes an infinite force, whereas with the Savox it took 8.4. And in addition to that, the new servo is completely waterproof, whereas the Savox is not waterproof at all. So I call that a win for my new servo, not surprisingly. The only downside it has is it's quite a lot heavier. It's about 700 grams, whereas the Savox weighs almost nothing. Anyway, I've got to put this stuff into the waterproof box to finish it off. And thanks very much for watching.